Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about magnetic refrigeration. So let's dive right into it. Well, first we have to understand the importance of need of cooling. Basically, we need it. It's not a luxury. Oh, I can live without it. No, we need it. We flat out need it, and it's a must for food and people at the same time. The sole reason we can have such a plenty in terms of food is simply because we can preserve them, and many foods require cryogenic preserve. Now, cryogenic as in like just cooler than like around 0 degrees Celsius for us to sustain us. That is a necessary. It's not a like, okay, it would be nice if we had it, not a big issue if we don't know. It's an absolute must, otherwise people will starve. Then people are, we as a human, we are a warm-blooded creature. We cannot just adapt with the temperature. So, and it has benefits, but it also has side effects. We need to cool down. So even though our body temperature could be as high as, let's say, 30 degrees Celsius, we're gonna be like, dude, we need 25 degrees Celsius to work optimally. And like our body has a heat rejection system, but it's not like magic. It still evaporates sweats out of us, and there's a limit to that. Like, and there are many people who lost their life due to heat stroke. So heat is very serious thing here. Now, because of the importance, because of the necessity of cooling, it became a very, very, very big power draw. Now, what is this quote-unquote cooling or quote-unquote cold? Now, scientifically, you have to understand this. There is no such thing as cold. All there is basically absence of heat. So when you say 30 degrees Celsius, that means there is 30 degrees of heat there. Not that there is like, some other aspect of it. Just that much is there. So for scientific reason, people talk about Kelvin. Kelvin because it's absolute. It's, aligned for 0 degrees. So there is nothing below 0 degrees. That is why we have what we call as absolute zero. Now, if what happens if you go below it, you can't. Physics will not allow you to go down. So that's the reality. Now, all of us, like in this planet, has a ambient temperature. So that ambient temperature, we utilize that for water, and that's why our thermometers are generally rated from 0 degrees Celsius, where water freezes, to 100 degrees Celsius, where water boils. Now, that scale should give you an idea that we do not actually just make it something cold, we just remove heat out of it. So how do you remove something out of it? You pump it out. You basically say take heat pump. That's why every scientific journal will always refer as refrigeration system as heat pumps. That's the reality of it. We are just pumping heat from a chamber, be it your room, be it a refrigerator cabin. It's taking heat in from inside and dumping it outside. That's all it's doing. Now, to understand the energy requirement, to understand the efficiency, you have to understand what we call coefficient of performance. Basically, you put 100 watt in does not mean you're gonna get only 100 watts of cooling. If your system is well designed, you're gonna take much more heat out of a chamber, and then you're gonna exhaust out. That's why whenever you have the condenser side, basically the hot end of the refrigerator, it's like so hot. Even though your room, let's say, was 30 degrees Celsius, the condenser side would be much hotter. Why? Because it's pumping heat from the evaporator side, so the cold side. So that's what we call coefficient of performance. So if you put 100 watts of energy into your compressor, you can get very high output of it. Basically at 3 COP, you're gonna get 300 watts of cooling. Now, if you are not familiar with COP, do not worry, it's a complicated thing. But if you have a refrigerator or air condition, I can guarantee in air condition, not in refrigerator, but in air condition, you can see there are plaques that are encoded with information. It will say 3 COP or 2.5 COP at 25 degrees Celsius. Now again, if the outside temperature becomes too hot, dumping energy into it becomes difficult, so you lose COP. But if it's outside is cold, dumping energy becomes very efficient. Now, inherently it does exceed 100% because all you are doing is pumping it, not creating it. That's why it has COP value. So you will like 3 COP. And if you want to use it as a heater, which many European countries are realizing that this is magical source, because a heater is only 100% efficient. This puppy can exceed that. This goes to 300%. So that's why we classify it heat pump. You are just pumping it. You are not creating it. You are just pumping it from point A to point B. Then we utilize that. It exceeds 100% of in terms of raw performance. What is the problem? If it works, it's more efficient than a heating system, then why the hell we have an issue? We have an issue because everybody needs it, and the biggest growth so far happened in the world is basically growth of middle class. Upper class remained the same way they used to be. Now the middle class, they grew exponentially. Basically, a middle class family used to be like, okay, 10% of the country's population. Then it became 35% of the population. At this point, it's even in poorer countries, it's reaching as 45%. 5%. So middle class is growing exponentially. So the people who can afford refrigerator and air conditioner went out like ballistic. It's like, okay, 100 million refrigerator, 100 million, 10 billion refrigerator. Like that's happened. So you have to understand the power consumption. Even when you are talking such a high efficiency, it's so much that we are consuming 1/5 of the world's power. Basically, if you take one is the power output of the planet, whole planet, every power plant combined, 1/5 of that is directly going for cooling. So you can understand, even if you can basically reduce power consumption by a small fraction, that would be like saving gigawatts of power on a planet level. So that is why there is like a labs, universities dedicated to just this, like just make our cooling system more efficient. Like if you make something more efficient by 1%, and 1% may not sound big for you, but like imagine basically a giant building whose air conditioning bill is like in megawatts. 1% for them, that's like, dude, that's hundreds of dollars saved. So that's the reality of it. And one of the primary things that you can easily assess where the heck energy is being lost is the noise and vibration of the compressor, because energy cannot be created nor destroyed. That means the noise and vibration is wasting energy. So, and because of the scale of it, saving even 1% is important. And in the early days, we were not very aware of the consequences of using CFC. Now, CFC was a very cool kind of gas. It did what it's supposed to do, but it was harmful to ozone layer. We punched a hole in ozone layer. And if this hole becomes very serious, it will literally annihilate farmlands. So you can understand this, we must have to fix. Like, it's not like, okay, we can ignore it like glow. No. You ignore this, you will run out of food flat out, because plants will literally either mutate or flat out die out, because plants have a certain levels of UV resistance. If there is no UV shield, forget about it. So that's the problem with it. Then we come to so many other options are there, and one of the options that have been getting a lot of request of is magnetic refrigeration. Now what the heck it was? Now magnetic refrigeration relies on a property of every material that has a magnetic dipole. Basically, if you can stick it with a magnet, it has magnetocaloric effect. Now this effect is very small, and every material has different properties to it. So to say, iron will behave differently in certain temperatures, and whatever you want to make has to behave in that temperature. So it's like a superconducting kind of scenario. You want superconductor at like absolute zero, or you want superconductor at liquid nitrogen temperature, or you want superconductor at minus basically liquid helium temperature. That's up to you. So whenever we are talking about magnetocaloric effect, it's present in all materials that are magnetic. However, you have to study this. It's like, okay, I want my refrigeration or air conditioner to work at around 20 degrees Celsius. Is your material works at that domain? If yes, awesome. If it does not, it's useless to you. So that is why people will always specify one material. Is like, this material has the most advantages or maximum impacts at this 25 degree temperature range. So what's happening here? It's basically a vapor compression system without any moving part. So what you have to understand, whenever you take a block of material, let's say you took iron, let's say you took it would be at ambient temperature. It will be like, you put it in a lab or put it in a slab, it will have the same temperature of surrounding. So it has 100 watts of heat. You put it inside a magnetic field. What happened is all the magnetic dipoles, they went from random chaotic nature to organized. Now when this happened, it lost the ability to contain heat. Basically, if it was a bucket that can handle 100 watts of heat, the moment you did this magnetic, it lost the ability. It's like, I can't hold this heat. It will dump that heat out. Now what happens when you turn off the magnetic field? Because this puppy dumped out the heat, and even though magnetic dipoles will rearrange into a quadratic form, it now is in negative form. Basically 100 watts went in, and now it's like minus 100 watts. Why? Because it dumped all the heat into the magnetic field. Now again, not as in like it creates magnetic field, as in like when the magnetic field was saturating it, it was dumping all the heat to ambient air. So once you disable the magnetic field, it's now cold because it has to absorb heat. Now it's at lower temperature than ambient. That's your refrigeration. So all that is happening on a magnetic dipole level. That's why there is no moving part. If you have, let's say, electromagnet, you can literally have like one side that is you still need some way of moving heat and cold. Like if you have heat pipes, you can literally do this. Like hot side directly goes to here, cold side goes here, and using electromagnets you can arrange this. So that's what's happening here. Basically, you taking a material, whichever alloy. Generally, materials are not that good. So if you take like iron, aluminums, and all that jazz, they do not have that too much power. However, you take certain alloys that are fine-tuned for that temperature. Let's say for air conditioning, 20 degrees Celsius is the ideal core. You take an alloy that is fine-tuned for that temperature, is gonna dump the most amount of heat. So this magnetic dipole, it's gonna absorb heat. You're gonna dump the heat the moment you quote unquote compress it during magnetic field. So it's happening in solid state. There is no compression, there is no vibration. So it's very efficient. So why the heck we want to do something like this instead of a vapor compression system which has been time tested and has a very high COP, as in like 2 to 3? Why the heck we want to use them? Well, again, it does not need a compressor. Compressor is a very complicated piece of equipment. Because we have learned how to mass produce it, it does not, oh, it's just a big black box, but it's a very complicated thing. So if you can simplify that, that has benefit. So once you simplify it, once you figure out mass production, the price will go down drastically. That itself is an advantage. On top of that, you do not need any gas. So this refrigerator, there is some other wine refrigerators also that was made for this, and all they had was water to circulate the heat out to the outer world and circulate cold into the inner world, basically the chamber inside. You do not need gas, and there are certain designs which allow you to do it solid state, but you won't even have water pumps that are circulating the coolant, so to say. And it has higher efficiency than compressor system. So that's why we want to do, like, even if it's like, let's say 10% more higher, like mathematical models suggest as high as 30%, and let's say in your real world, real engineering and all that jazz, you achieve a point where it's like, okay, 15% more efficient. That's like megawatts of power saved per small building. That's a lot of energy saved. So that's the reality of it. Even if we can save just a little bit and we do not have to use harmful gases that will be dangerous to our atmosphere, that's like, awesome. Now let's come to the reality of it. Now reality, the vapor compression refrigeration system has an energy consumption for the compressor unit. Now you take that compressor alone and it's like, okay, this is the compression. What should be the mathematical best output? You take that as like, okay, 100%. That's the mathematical output. The reality that we have right now, we have already achieved 60%. And there are certain systems where you can push even more. Now small refrigerators, they are really not that good. But when you are talking about like big scale, commercial scale units, they are 60% efficient. So we are very close to as much we can get out of realistically speaking. But the moment you talk about magnetic refrigerator, it does not even come close. Now on paper, magnetic refrigerator is awesome, amazing and all that jazz, but in reality they do not have any, like, it does not even hold candle to it. Simply because, again, there are all the papers I've studied, there are like hundreds of reasons, primary of which is magnetic hysteresis, basically magnetic domain. If you are like, okay, let's say a domain supposed to be like this when it's outside of a magnetic field, and like this when it's inside the field, at some point after doing this again and again, it will get stuck at like this, like half. It will no longer have the carrying capacity, and that happens on magnetic dipole level. So your whole material, which has the ability to carry, let's say, hundreds of water feet, it will reach a point in like as few as like few hundred cycles, reach a point where it's like, yeah, I can't carry anything. And because of the realization, like how to actually make this stuff, it was required like multiple pumps, multiple valve systems, all that jazz. And reality was, it ended up more inefficient than the compressor system. That's why, because compressor system, we have already learned and refined it to nth degree, and it's one thing. The whole vapor system only has one moving part, which is the compressor. That's it. There is nothing here. Here they're like, all designs has like, okay, we're gonna have magnet and that's gonna rotate, and we're gonna have fluid system which has to change because the magnet that itself is becoming hot, it itself is also becoming cold. So you do not have two sides. You have one thing that is becoming hot and cold. So you have to have a way, okay, during hot side I'm gonna connect it to something else, during cold side I'm gonna connect it to something else. You can understand that is tangibly complicated to deal with, where in a vapor compressor, hot side and cold side, put hot side outside, put cold side inside, done. So reality is, like, whenever somebody actually wanted to build something like this, can they build it? Yes, there are companies from Japan, America and Germany, all of them built it. I have provided the video down below. They built it, but reality was, it always ended up with more complicated and more inefficiency than the compressor based system. So that is why, like, in practical, like, this is a compressor, it has like multiple piping system and multiple who has to make sure that it actually works. So the reality is, like, it is one of those things which makes sense on paper, like, if you are not digging too deep into it, and once you actually start building it, now it has some use. Magnetic refrigeration is not dead. It's used in cryogenic industry, because at that temperature it becomes yellow. But again, we want a refrigerator to work, let's say, minus 20 degrees Celsius, not minus 200 degrees Celsius. So at that temperature is pointless. So that is why you cannot, like, whenever you see videos about magnetic refrigeration, it's like, it's gonna save 30% electricity. Yeah, no. And I've been seeing this from 2015. Japanese company has achieved this like around 2010, and even American companies, like, the whole technology is there. It has been used. I mean, cryogenic industry is kind of necessary, but practical for home, everyday consumer use, it flat out does not even come close to the 60% efficiency of vapor compression refrigeration, and it has way too many moving parts. So even though you do not make sound as intense sound as a full-fledged compressor, you're still making a lot of moving parts, still having more points of failure. Reality just does not support it. So this is one of those things where, like, everybody thought it, like, everybody jumped into the jump wagon, and in reality it did not turn out to be true. So This was my presentation on magnetic refrigeration system. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.